Okay, everyone, good afternoon. Today I'm going to go over a topic that we briefly covered in here, but I'm going to go through it in a little bit more detail. It's sequential logic. So we had previously talked about how there's combinational logic, which is where you have the output as a function of the inputs. And in System Verilog, you implement combinational logic through a concurrent assignment statement or through like always underscore comb. And then there's sequential logic, which is where the output is a function of both the inputs and some kind of input history. So sequential logic implies that there's a memory of some kind in your circuit. And we've used this already. We've implemented sequential logic using always underscore FF at pause edge clock. We did this in the test bench, and obviously in the CPU, we have sequential logic for the registers, like the program counter and the GPIO out and the register file. But we haven't talked a whole lot about it yet. We just kind of gave you the details you needed to get the CPU designed. And you might have talked about this, hopefully you did a little bit in 2.11 as well. So sequential logic is kind of a broad term that describes logic, as I said earlier, logic whose output depends on past inputs, but sequential logic doesn't necessarily need to involve a clock. You could just have a case where you have like a cross-coupled gates, or logic gates with a feedback. The way that you can implement, if you've ever seen a latch designed with cross-coupled gates. A more specific term is synchronous sequential logic, which is a type of sequential logic that has a clock involved, and that's the type that we use in this class. I've never actually tried to create non-clocked sequential logic on an FPGA. Maybe possible, but it's not something you typically do. And then asynchronous sequential logic is when you have sequential logic that doesn't involve a clock. And when I was in undergraduate school, we talked about this a lot, I think, because there was a thought that in the future there would be a lot more asynchronous logic. That's when you have logic that's cross-coupled, where you have outputs of gates feeding back into the inputs, but it's designed in such a way where the circuit is designed to be stable in the sense that the state of the circuit would change only when you have an input changes. So in other words, the state would be changing on whenever one of the inputs changes. And in fact, there are some examples of this. For example, IBM had a chip I guess it's been about 10 years ago now, called the IBM True North chip, which was a neuromorphic processor. It was basically an array of reconfigurable spiking neurons for a neural network. And it used asynchronous logic, where it didn't have a global clock. The neurons were triggered on pulses from their inputs. So this is, every once in a while you'll see a chip with asynchronous logic, but it's fairly rare. So I'm going to be focusing on synchronous sequential logic, because that's the most common type you see in processor design. And it's the type we use for the CPU. And so there's some other terminology. So whenever I say state, you can think of state as basically like the memory inside of a sequential logic circuit. But what it means is it's all the information required to explain future behavior. So when you design a sequential logic circuit that's not just like a RAM or a register, the state is a concept that you have to incorporate into the design. And I'll talk more about that here in just a minute. And then latches or flip-flops are what holds the state. Those are the memory elements that you'll use to hold the state. And of course, the difference there is latches are level sensitive, so they're active on the whenever the clock is at a certain level, high or low, whereas flip-flops are edge sensitive. Those are the ones that we're using in the class. And I talked a little bit about previously the difference between how latches and flip-flops work. Registers, as I mentioned, contain the state, and if you're using the flip-flops for your state, then then the state will change on the rising or the falling edge of the clock. So when you're designing a synchronous sequential logic circuit, and when I say circuit, by the way, what I really mean is HDL, right? When you're designing the HDL. And of course, this is the circuit that's generated from the HDL, that's synthesized from the HDL. So every circuit element is either a register or a combinational circuit. A register, again, is just a multi-bit flip-flop. At least one circuit element needs to be a register, because otherwise you just have a combinational logic circuit. All the registers receive the same clock. So, you have the clock come in, you have a top-level clock that comes in, and it just, fans out to all of the registers, creating a clock network. And every cyclic path contains at least one register to break the cycle. So we saw this with your stall signal. So, you're in your CPU, your control unit puts out a stall signal called stall fetch, and then we put a register in there between where the input was stall fetch and the output was stall EX, right? And the stall EX was a delayed form of stall fetch. So two common types of synchronous sequential circuits would be finite state machines and pipelines. And we've already, you've already designed a pipeline in Lab 3. So instead of talking about that, I'm going to talk about the other type, which are finite state machines. So the idea with a state machine is it's a circuit. I've talked a lot about how, like in System Verilog, the order of the lines of code doesn't really matter, right? It doesn't matter what order you put in, like an assign statement, because every assign statement and every always block is a circuit, and they all operate concurrently. Now there is some things in System Verilog, like you have to declare signals before you use them, but that's just a rule they made up in the language, right? But in general, your circuits are all operating concurrently. But what if you have to introduce some kind of sequential behavior in hardware? Like you need to have there to be a sequence of things that happened over time, right? And this commonly comes up in things like bus controllers, right? Where you have to go through phases, where you have to first request access to a bus or request mastership of a bus, and then there's some kind of an arbiter that has to come back and grant you access. So kind of like a handshaking type of procedure, right? Whenever you have to handshake. Or whenever you have to read data across multiple clock cycles and do something with it, like for example, a serial to parallel converter, for instance, where you're taking bits and you're trying to assemble bits into a parallel bus, individual bits into a parallel bus. So those are the kind of things that you use finite state machines for. And there's two styles. There's a Moore machine, which you define these states the circuit could be in. So in the case of a bus controller, your states would be something like idle, like nothing's going on. And then you may have a state like that you go into if someone's requested access to you, but they're waiting, for a response back, or they're waiting for it to be granted, right? Those are states. And so you define your set of states, and then your outputs of the circuit could be a function of what state you're in which case the outputs can only change once per clock, right? Or your outputs could be a function of the state and the inputs, which means that basically what that means is that every state is defining its own truth table, meaning that once you're in a state, you can change the outputs or the inputs, and the outputs will update immediately, right, in principle, meaning that the outputs are asynchronous with respect to the inputs, right? So in this lecture, I'm just going to focus on the simpler type, which is the Moore machine. The way that we remember this when I was in school is that, more is less, because more is the simpler one, right? Okay, so let's look at, this is an example from the textbook. I'm not really crazy about this one, but it's a fully worked out example. So the idea is to create a traffic light controller. So we're going to have basically an intersection with a traffic light, and we want to design a controller that'll control the traffic signal where it essentially has two inputs. It has the clock, of course, and then it will have traffic sensors at each of the two roads that are crossing, right? And so the inputs here will be traffic A, traffic B, that's the sensor. The outputs are light A and light B, which are what we want to light it, what color we want to make the light on that street. And then of course there's the clock and the reset. And the reset, you typically will have a reset there that will, be used to put the state machine into a reset state, a sanity state, right? Okay, so the names of these streets are, it's A and B, or A stands for Academic Avenue and B stands for Bravado Boulevard. And so the states represent essentially which street we want to have flowing and which street we want to stop, right? So there's essentially two states. We want to have a green light on Academic and a red light on Bravado or vice versa, right? However, there's two additional states that are used for the yellow light configuration. So before we change from green to red, we'll have a yellow light transitionary state in there as well. So in total, there's 4 states. There's a state 2 for the green light on either road and 2 for yellow light on either road. And of course, the other road would be red. And as I mentioned, the traffic, the inputs, there's a one bit input for the traffic sensor on Academic, and a 1-bit input for the traffic sensor on Bravado. And we're not specifying which side of the intersection. We're just saying, if there's any traffic waiting on any traffic on Academic or Bravado. And then the clock cycle. Now, normally your clock is going to be, like megahertz or gigahertz, right? But in this example, we're assuming that the clock is really slow. In fact, it's so slow that the clock period is going to equal the time that we're in the yellow light state, how long the yellow light's on, right? So it's like a, 5-second clock period, right? Really slow clock. And then the lights, there's LA, L sub A, L sub B, which is what color we want to make the lights, and those are a trinary, there's 3 states, red, green, and yellow. So each of those would have to be 2 bits in order to represent the 3 light colors. Okay? And so we have to start out with a reset state. So we just have to make a decision, which light is going to be green when we bring the system up. So in this case, Academic is green, Bravado is red on our reset state. And so you typically, there's no standard way to do this, but typically the reset state is going to have a little arrow in it that points to it with reset, or sometimes there'll be a double circle for the reset state. And so we're going to give the state a name, S0, which is just arbitrary. We could have called it like Academic Green. We could give it any name we want, but S0 is just a symbolic name we want to give it. And then the outputs are listed in the state, and this is something you do for a Moore machine, because each state will only have one set of outputs, right, in a Moore machine. If this were a Mealy machine, the outputs would actually be on the outgoing transitions. But just for now, since it's a Moore machine, we're going to put the outputs. Each state will have its own output. So we're going to have light on Academic is green, light on Bravado is red. Okay, and then we'll add 3 more states. So this ends up becoming a graph, a directed graph. And so we have our 4 states. They're labeled S0 through S3. And then we add the transitions. The transitions designate how one state can be transitioned to another, or how one state becomes another as a function of the inputs. Now the problem with this is that how many transitions should be coming out of each state? Well, it would have to be like 2 raised to the power of the number of inputs, right? So we have two inputs, traffic on A, traffic on B, right? And those are binary. So there ought to be 4 transitions, 4 arrows coming out of each state representing all 4 of the possible permutations of input values, right? The problem, though, is that gets a little hard to read when you have all those arrows. So typically what you'll have on here is a shorthand, and also sometimes some of the inputs are don't cares. commonly. So what's happening here is that if we're in state S0 and I have traffic on academic, and the green light is on academic, I want to stay in that state, right? So when the clock edge, next cycle comes, we're going to stay in there. And so there's that loopback connection, right? And then if there is no traffic on academic and the green light is on academic, then we should begin transitioning over to putting the green light on bravado. Of course, we have to go through the yellow light state first, okay? Now you'll notice that there's no arrows referencing TB, traffic on bravado. Why? Because, well, we don't really know why, but we can assume that there don't cares. We don't care. So if there's so this transition is based on essentially waiting for there to not be any more traffic on the street with the green light. That's the idea. So we don't care if there's traffic on the red light street, which is why there's no arrows coming out of here that have TB, right? So if with no traffic on academic, so that we have not TA, then we'll transition to the S1 state where we put a yellow light on academic, and of course bravado is still red. And then here there's actually an unconditional transition coming out, meaning that both inputs are don't cares. And so we're just going to stick around in that state for one cycle, right? Which will be the amount of time that we're in the yellow light state, right? And then we'll come down to S2, in which case we've got a green on bravado and a red on academic, and we're going to stay in there for as long as we have traffic on bravado, right? And not caring about cars lining up on academic, right? Which is a bad design, obviously. There should be some kind of a timeout here, too. There should be another input with like a timeout counter that will limit the amount of time we're in any one of these, green light states. But that's not in here, just to make this simpler, right? And then finally, once we've reached the point where we've got no more traffic on bravado, we'll transition over to S3, where we'll turn the light yellow on bravado, and then for one cycle, right? That's our yellow light period, and then we'll go back to S0. Okay. So the point of this is now obviously, let me clarify a few things about this. So first of all, if you were designing a traffic light controller, you wouldn't do it with a state machine. I mean, not a hardware state machine. You might do it with a software state machine, right? You might implement this in software, but you'd have some kind of microcontroller running in there, right? Where you could put, because it's a lot easier to design software than it is hardware. So why would I try to do everything in hardware, right? Especially since it's not like I need it to be really fast. The clock is running at like a 5-second, period here. So this is, you would never design something like this in pure hardware. As I mentioned, it's more commonly the case that you would be designing state machines to control arithmetic in a circuit, right? Like, for example, I don't know if you guys remember this, but I mentioned, why don't we use a divide instruction in this class? Why don't we have a divide instruction in the ALU? Because the divide instruction would, most likely, if you do a divide, it would be a multi-cycle divide, right? It would perform a divide. It would divide A divided by B on your ALU, but it couldn't be done in one cycle, because doing a divide in one cycle would be very expensive, and it would take a long time to synthesize that, and it might eat up your whole FPGA. So the divide instruction can be generated in Quartus if you want. You can generate a divider, and you can have it generate a multi-cycle divider where it goes through a sequence of steps. The controller that controls that divide process would be done with a state machine like this, right? So that's the more common type of state machine you'd have, would be controlling a divider circuit, right, for example, multi-cycle divider. Okay, but yeah, this is just, the traffic light example is just used as an obvious example for explaining how you create these states and transition between states. Okay, so how is this implemented in hardware? So I mentioned earlier that a state machine is comprised of some combinational circuits and then some registers. So the question is, how do you assemble everything together to make this work? Now obviously, if you do a state machine in Verilog, a lot of these like truth tables are generated for you as part of the synthesis process, but this is explaining how that works. So basically you need to have a next state table, right? You need to have a truth table or a combinational logic circuit that will calculate the next state as a function of the current state and the inputs, right? But this is purely combinational. There's no memory here. This is just giving us the next state. The next state isn't acted upon until the clock edge, in which case the next state becomes the current state. So in this case, we're still enumerating these states as symbols, S0 through S3, and we create this truth table. Now normally, this truth table would have how many rows in it? It would be 2 raised to the power of the number of inputs. In this case, the inputs are the current state and the inputs, right? So there's 2 1-bit inputs, and the state must be 2 bits, right? Because there's 4 of them, right? There must be 2 bits to encode, at least 2 bits to encode these 4 states. So there ought to be 2 plus 2. There ought to be 2 raised to the 4 rows in this table, right? There should be 16 rows, but we only have 1, 2, 3, 4. There's only 6 rows in this table because we're taking advantage of these don't care values. So these don't care values, anytime you have a don't care, that you could expand a 1 row with a don't care into multiple rows, right? In fact, 2 raised to the power of the number of don't cares. So this 1 row, since there's 2 don't cares, actually, comprises 4 rows, right? But luckily, we've got some don't cares. We can keep this really simple. So in this case, we have 1 row for each of the arrows. Each of the arrows, each of the transitions has 1 row for it in here, right? So each one of those arrows in the graph has 1 row. And then, so if you're in S0 and you get traffic on, no traffic on A, then obviously your next state's going to be S0, right? We're going to stay in S0, right? If you're in S0 and you have traffic on academic, then you're going to want to go to S1, right? So you can fill in those values as such, right? So yeah, so basically you just look at all the arrows in your state machine and you just use those to build the table. And then, as I mentioned, there's 4 states. You need to have at least 2 bits to map values. You have to have actual binary values for the state values. You have to associate them with binary values. So we do that here. So S0 is just 0, 0, S1 is 0, 1, S2 is 1, 0, and S3 is 1, 1. Nice and simple. And so basically all we're doing here is substituting those states, those state values for the state symbols. And then once you have that, then you can just use your knowledge from your skills from 611 to take the truth table, and you can then convert this to Boolean logic, right, for the next state. So notice that the notation here is the S sub 1 prime is the next S1, what it'll be in the next cycle. And so there's S, that's the next state. So the next state is the output, the current state is an input, and then of course the traffic sensors are TA, TB. Now S1 is actually, in this case they have S1, next state of S1 is S1 XOR S0. Is that true? So if you look at these 3 rows where S primes sub 1 or S sub 1 prime, right, the next state for S1 is pretty much just going to be those 3 are when you have a 0 and a 1 on S1 and S0, right? So there's S1 XOR S0, right? Okay, so then what about the output logic? So the output is, because it's a Moore machine, the outputs are calculated just on the current state. So we just need a table that will create the output logic where the inputs are the current state and the outputs are the light value for academic and bravado, which again needs to be converted to Previously we just showed it as green, yellow, and red. So we'll assign green to 0, 0, yellow to 0, 1, and red to 1, 0. And then so you can substitute those in the table. But now you've got 4 outputs, 2 bits each for the light at academic and the light at bravado. And to figure this out, you would just go back to the state diagram. And in this case, you're not looking at the transitions. You're just looking at what's inside the states, right? So there's the name in the states and the outputs are in the states. So you can build this table, and you can also then convert this table into Boolean logic. Okay. Okay, so then we have the next state logic and we have the output logic. So we have 2 of the 3 pieces we need. The final piece is the actual memory, the flip-flops. So that's typically called the state register, or in Verilog it's called the clocked process. It's the clocked part. So there's those other 2 parts are just combinational. This is the only sequential part of it. Essentially it's just a register where the input is the next state and the output is the current state, right? And of course you connect the reset. Now, by the way, let me revisit the reset thing for a second. So the reset state is assuming that the reset on the flip-flops resets them to 0, then the reset encoding has to be all zeros. So you can assign the states to whatever codes you want, but you have to be careful that the reset state has, is all zeros, right? And S0 is 0, 0. So we're good. We're good there. Okay, so then if we're doing that, so let me skip ahead here a minute. Okay, so this is the digital logic design then for the next state logic and the flip-flops, the state flip-flops or the state register. So this, notice we have that's an XOR gate, right? Because remember that the next state for state bit 1 is just the XOR of the old state bits, right? Make sense? So S sub 1 prime is going to get S sub 1 XOR S sub 0, right? And then the other bit, S prime sub 0, is this logic. We just converted the Boolean logic to gates. And so you have this next state logic feeds to the Q the D input on the register here, and then the Q output is coming back around and being used as inputs to the next state logic. Okay, and then the output logic looks like this. So the output logic, there's no, this is just taking this S1 and S0 and putting that into logic gates to generate the light signals. Okay, so that's the digital logic, the Boolean logic version, digital logic version. What about the Verilog? So if you're doing this in Verilog, you still use the same. You still decompose this into the same 3 pieces. But there's a couple strange things here, though. In Verilog, you would have to decide your state encodings yourself. You would have to use parameters, which are basically constants. You'd have to decide what bit binary values you wanted to associate with each state. You had to do that. System Verilog fixed that because they introduced the ability to create an enumerated type. So we have type def enum logic 1 down to 0, S0, S1, S2, S3, and we're going to call that state type. So that creates a new type called state type that can have the value of S0 through S3. You still have to tell it that it's 2 bits, though. But by creating this enumerated type, you're allowing the synthesizer to decide how to encode those state values. right? And so you don't have to worry about that. And then you have to then declare your current state and next state as two signals of type state type, right? So those first two lines just set up the states, and then they create the current state and next state signals. Then you have this little short always FF that does nothing other than takes care of the reset and putting the next state into the current state whenever you have a clock edge. And so regardless of how large your state machine is, this part will always be essentially 4 lines of code, right? Because every state machine will have this, this little part that puts the current state in the next state, right? Okay, then you need your next state logic. So in this case, I broke my own rule. I think I told you guys that I prefer to use assign statements for combinational logic. But in this case, I'm using an always comb with an if statement. And you could use a case statement in here too, since it's an always, right? Or like I said, you could use an assign statement here. But this is purely combinational logic. So it's just essentially some way of taking the current state and the inputs and setting the next state. And so there's many ways you can do that, however you want to build your next state behavior, right? One nice thing about, well, even if you use an assign, I mean, one thing about this you'll notice is that it's simplified. It takes advantage of the don't care. So it says if the current state is S0 and traffic at academic is 0, then my next state will be S1, right? Now, one thing that you keep in mind here is that what happens if we know that the current state only changes once per cycle, but the inputs don't necessarily have that restriction. So what may happen is that if you're in state S0, the traffic at the academic light or academic avenue, the road traffic sensor, it may toggle up and down several times within a clock cycle. But this logic won't notice that. It only cares what the traffic is, on the rising edge of the clock, right? Because what will end up happening is if that traffic sensor is glitchy, right, then the next state may change multiple times inside of the clock cycle, but only matters at the end of the clock cycle when I bring my next state into my current state, right? Okay. All right, so that's the next state logic. And then finally, you have the output logic, which is just another combinational logic. You can make this with an always com or with an assign. And if you do, again, if with an always com, you can use a case statement. It's pretty common to use case statements for these. And this just, in this case, I set a default value for academic and bravado. I set them both to green, which, you might think, well, that's kind of dangerous. But the way that the if statement is structured, it will always change. One of those won't be green, right? One or both, right? It may change them both, one red and one yellow, right? But I just set the defaults to green, so that way I only have to set the output that's not green inside the if statement, right? So it simplifies that code. Make sense? Any questions about that? Now, some people will combine the next state logic and the output logic. You could put those in one always if you want. You can combine those. You don't have to have 3 separate always. Or like I said, you don't have to have, you could, or even, you could have a clocked, which has to be always the clocked process. And then you can have, 2 assigns for the output and next state. Or you can, sometimes they'll combine next state and output logic into one always. I don't like that though. I like they used to call this the three process FSM, which is where you have 3 separate processes, process being an always statement. In VHDL, it's actually called a process, but it's equivalent to an always statement. Okay, so if you simulate this, now there's something here that's gets a little confusing when you simulate. So you'll notice that we have a reset pulse at the beginning, and that gets us into our current state becomes S0 in response to the reset. Okay, and because of that, we have a green on academic and a red on bravado. And our next state is also S0, but that's only because TA is high right at the beginning. We have traffic on academic right at the beginning. If that TA had been low there, then we would start out with being in S0 for only one cycle, right? But because the traffic on academic sensor was like initialized high, we're going to stay in S0 for a little while. And basically, we're going to stay in there for as long as we've got traffic on academic. Eventually, the traffic will stop on academic, in which case our next state will become S1, right? And then eventually, the current state will become S1. And this is the part that I find to be a little confusing. Because what's happening here is that you're always going to see this one cycle delay between your input and your state change, right? Generally, assuming, of course, that your inputs are changing on the same clock edge as your state changes. Now, I think, actually, let's see, where is this rising? Rising. Yeah, this is rising active. I can tell because when you see S changes just after the rising clock edge, right? So this is a rising clock edge system. Now, the traffic sensors, though, are asynchronous. They don't have to change on the clock. They don't have to change on the clock. Now, typically, when you design a system where you've got multiple state machines talking in a circuit, usually things will be changing on the same edge of the clock because the inputs are typically coming from another sequential logic circuit, right? But in this case, I think the implication is they're coming straight from the sensor. And that's a problem, by the way. We'll talk about why that's an issue when we talk about timing analysis. But when do these change, by the way? Traffic sensors, you could tell, are changing on the rising edge. See that? Rising edge changes. This guy changes on the rising edge, right? Now, this diagram also is putting a little logic delay in there, too. A little bit of logic delay. You see that the dotted lines represent the rising clock edge, but notice that stuff is changing to the right of the dotted lines because they're trying to simulate a little logic delay. If this were in Model Sim or Questa-Sim, you wouldn't see that logic delay. It would be invisible because by default, there's no logic delay in Model Sim. Everything's happening instantaneously on the edge, right? You guys with me? Okay, so what happens is we start out in S0. We get some traffic on bravado here, which is ignored, because that's how the circuit is designed. Traffic on academic, though, goes from 1 to 0, and that's when we finally begin the transition to the green light on bravado, but of course we have to go through S1 first. The yellow light state is S1 and S3. You'll notice that those are always one cycle because there's an unconditional transition out of there, right? And then we go into S2, and in S2 we're waiting for traffic to die down on bravado before we make a change, right? So you'll notice bravado traffic stops here. That indicates that instantly changes the next state, but the current state waits another cycle before it updates, right? Make sense? So there's always this delay, which, like I said, this is the most confusing part, and I'll show another example in a bit why that's confusing. Any questions about this? Okay. All right, so let's, oh yeah, so the way that the states are encoded, the state encoding affects the logic for the next state logic and the output logic, because these two Boolean logic expressions depend on how we encoded the states. So this logic would be different if we applied a different encoding to the states. This is the reason why in System Verilog they wanted to give the programmer the ability to use enumerated types for the state, because then, presumably, I don't know if it actually does this, right? But ostensibly, the synthesizer is going to pick encodings that will give you the minimal logic here for the next state logic and the output logic. Does it actually do that? I don't know. I doubt it. I have my doubts, right? But if you had to do it, then you just assign arbitrary state values, and then you may end up with a circuit that's more complex than it needs to be in terms of number of gates, right? Now, when I was in school, they told us that the best state encoding is actually not to use binary, but to use unary, also known as one-hot encoding, which is where if you have n states, then the state variables should have n bits, and you just put they're all 0 except for a 1 in a specific bit position. The theory is that if you did that, you would get the minimal next state logic, right? I've never actually seen a proof of that or even seen that in action, but that's called one-hot encoding. But that was the conventional wisdom, is that you should use one-hot encoding when you assign. The problem is that in System Verilog, it's not going to be able to use one-hot encoding unless you give it enough bits up here when you declare the enumerated type, the enumerated state type. Notice that I'm only giving it 2 bits, so it's not allowed to use one-hot encoding. Otherwise, it would need to have 4 bits for that, right? But that's also something that's up to you. Okay, so I'm going to go through a couple more examples here. This was an example that I came up with for an exam that I gave back in 2018. So you're designing a controller for an elevator in a 2-story building. The controller has the following inputs provided by the buttons outside the elevator on each floor. So you've got 2 floors. So since there's only 2 floors, you can only request up from floor 1 and down from floor 2. So there's only 2 inputs to make that simple. And then the inputs inside the elevator are just floor 1 and floor 2. And then the controller has 2 outputs to say go up and go down. And the clock cycle is set to be the amount of time it takes to have the elevator move from one floor to the other. Okay, so the idea is that you need to come up with, the main objective here really was to just come up with states. And so what are the states in this system? Well, you have to obviously have, the elevator's got to know where it's at. So there's got to be a state for its current position. It's got to track itself. But also, you also have to have an additional piece of information telling it what it's doing. What is it? Is it idle, or is it in a state of change, right? So I had a state called first floor idle, which was my reset state. And then I had a state first floor, I'm on the first floor, but I'm moving up. And then I had a second floor, I'm on the second floor, but I'm idle. And then another one where I was on the second floor and I'm going down. And so the transitions here are based on the buttons inside the elevator and outside the elevator. So if I'm idle and someone in the elevator hits F2, or if someone outside the elevator on floor 2 requests the elevator, right, then it would move up, right? At which point it would set the GU to 1. That's the motor that, activate going up. And then if you're on the second floor and you're idle, then likewise you would wait for someone to push the button inside the elevator to go down, or someone push the button outside the elevator on the first floor to call the elevator, right? And so those were the inputs, and every other input combination would be a don't care, because the elevator is going to ignore any other input, right? So that was the, again, if you were designing this in practice, you would be doing it on a microcontroller with software, but this is, the idea here was to come up with what these states are. Okay, so, yes, this is already talked. This is an example. This is the same thing. Another example, but in this case we have a case state for the next state logic. So this one is a divide by. This is a different application though. This is a divide by 3 counter. A divide by 3 counter is a counter that counts from 0 to 2 and back to 0 again. So as opposed to it rolls over at a non-power of 2, in this case 3. And so in this case we have 3 states, but the states all have unconditional transitions to the next in the sequence. So this is just counting from 0, 1, 2, and back to 0 again. And so you'll look at the next state logic here is all unconditional. In this case, I use the case statement, though. It's fancy schmancy instead of an if statement. And then the output logic is, in this case, I'm only going to create a pulse whenever I'm in state S0. So what will end up happening is I'll have a clock that runs, and that pulse will happen only in 1/3 of the cycles, right? So the output logic, nice and simple. The next state logic's all unconditional. And then, of course, the clocked process is that same 3 or 4 line code. Make sense? Okay, so that's a real simple one. How about the example that I covered in class when I was reviewing for exam 1? So this one was from ChipDev. This was a rising edge detector, and it asked to detect, you have one input and one output, and the goal is to pulse the output whenever it detects a rising edge in the input, right? So there's a couple different ways you can do this. So my solution in class was to just create a shift register that would keep track of the last 2 values of the input, right? And then you could use combinational logic just to set it to 1 whenever the current or the most recent input is 1 and the one before that was 0, right? That would be a rising edge. You can also design that with a state machine, which is the way they did it on the solution on ChipDev. And this is where things start to get a little complicated, though, in terms of picking states. So the way I did it was I created one state to represent the last 2 input values. So I have a state 0, 0, which meant I have the last 2 inputs are 0, 0, right? Now, this is where that delay comes into play, though, because if I'm in state 0, 0, that's also the reset state, too. That's why I used a double circle there to indicate that. But if I'm in state 0, 0, it's not recording what the current input actually is. The 0, 0 represents the value that was in the last cycle and the cycle before that, right? Because it takes a cycle to update the state, right? So the state, this is saying that the last 2 inputs were 0, 0, but it's 1 cycle old information, right? So then you create the state diagram, and this one is fully populated with transitions. I don't have any don't cares in here. I've got 2, so there's only 1 input, luckily. So I have 2 transitions coming in at each state. So if I'm in 0, 0, and I get a 0, I stay there. If I get a 1, I go to state 0, 1, which probably should have been 1, 0. But in this case, the 1 there, the right bit is the one that was seen most recently, and the left one is the one that was seen less recently, right? But on second thought, I should have swapped those. But anyway, if I get a 1, I go here. If I get another 1, I go to 1, 1. If I get a 0 from there, I'm at 1, 0. If I get a 0 from 1, 0, I go back to 0, 0, right? And then all I have to do is figure out which state is the one that I should pulse to have an output of 1 that represent a rising edge. So the rising edge would be, what? I have it on 1, 1. Probably should have been 0, 1, right? Might have a typo there. 1, 1. Yeah, so if I'm in 0, 1, I would have seen a 0 most recently. No, that's right. Yeah, because I would have seen, no, actually 1 would have been most recent. Yeah, I think I do have a typo there because remember the right one is the most recent one. So I should have had any state with a 0 in the right position, and then I get a 1. So basically, if I'm in, no, 0, 1. Yeah, I'm confused. I got myself confused here. So if I'm in 0, 1, I would have had a 1 and a 0. That would have been my rising edge. And then, so probably I should have had a 1 here, actually, right? But that still would have given me a, yeah, I think that's what happened. That should be D out equals 1 there. I think what happened is I got the output wrong, right? So that should be D out equals 1, and these other 3 should be 0, right? Now, the thing about this, though, is keep in mind you've got that delay. So if I get a rising edge, so where's my rising edge? My rising edge is here. I got a rising edge here, and I got a rising edge here on Dn, right? So those are the two events that I'm trying to detect here, right? And so I should have a pulse on my rising edge, right? So in this case, I get a rising edge here, but it's going to be a 1 cycle delay before I can have that pulse, because it's going to take 1 cycle for me to notice the pulse in a Moore machine, right? Make sense? So notice I am right there. So S01 should be a D out 1, right? Notice that the S01 has a 1, right? S01 has a 1, yeah, so I need to fix that. Make sense? So what's happening here is I've got a, again, 1 cycle after that rising edge, I get a pulse here. 1 cycle after that rising edge, I get a pulse here. Any questions? Okay. There was something else oh, yeah, notice too, I've got nothing in these first 2 cycles, nothing, right? Because I don't have a reset. I didn't reset it in here. So I don't know what the state is. You know, basically, because I have 2 bits of state, and I don't know where I'm starting, I don't know what the initial condition is, right? So I don't know what state I'm in until I have 2 cycles of samples here, right? So by the time I get that clock edge and that clock edge, I'll finally know that I'm in S00, right? So basically, I've initialized this to state 00, not through the reset, but by having the input at a known value for 2 cycles, right? Okay. Okay, so here's another example from chipdev.io. I like this one. This one is, I think, pretty tricky. Design a circuit that determines whether an input value is evenly divisible by 3. Okay, so before this, I had a divide by 3 counter, which basically just counted and gave you a pulse every 3rd cycle, right? But this one's different because this one has an input value. And so the idea is that I'm shifting bits in serially, right? And I'm building a running value through doing that. So I start out with 0 on a reset. If I shift a 1 in, I'll have a 1 in there. And if I shift another 1 in, I'll have 3, because there'll be 2 1s, right? And if I shift a 0 in after that, I'll have 6, because it'll be 1 1 0. So in general, the way this works is every cycle, you basically take your running sum and multiply it by 2, because you shift it 1 bit to the left. But then you either add 1 to that or not, depending on if the input is 1 or 0, right? So if my running sum, say, is 17, right, and I put a 0 in, then in the next cycle it's going to be 34, right? But if I put a 1 in, it's going to be 35, right? So that's what I'm trying to show here, is that I start out with 1. If I put a 1 in with a value of 1, then my value is going to be 1, right? My input is 1. I'll get 1. If I put another 1 in, I'll get 3. If I put another 1 in, I'll get 7. But then if I put 0 in, I'll go from 7 to 14. And if I put another 0 in, I'll get 28. And if I put a 1 in, I'll get 57, because 28 times 2 is 56, and then I add 1 to get 57. Then if I put 0 in, I'll have 114. If I put a 1 in, I'll get 229. So that's how the input works. But the objective here is to then have an output bit that is 1 whenever the value in the running sum, the running sum, whatever you call it, is evenly divisible by 3. So of these values, 0 is evenly divisible by 3, 3 is, 28 is, 57 is, right? The other ones are not, right? So how do I design a circuit that keeps track of whether this serially shifted in value is divisible by 3? So it took me a while to figure this out. This was, and this is a waveform that's from the website that shows an example. it took me a while to, this is a tricky one. So the way I came up with the solution, I don't know if this is the best way to do it, but I thought of it as a tree where you start out as 0, and then if you get a 1, if you have another 0, you just stay in 0. Oh, and the red ones are the ones that are divisible by 3, right? So if I'm in state 0, I'm divisible by 3. If I get a 1, I have 1 value, it's not divisible by 3, at which point I can go to 2 or to 3, right? From 3, I can go to 6 or 7. From 6, I can go to 12 or 13, right? So you look at this and you're like, okay, I've got 16 states, right? I mean, obviously you could keep growing this tree out, right? But I've got 16 values, 0 to 15. How many of them are divisible by 3? 1, 2, 3, 4, 5, 6, right? So roughly a third, right? Now, how do I figure out how many states I need in my state machine, though? Well, it looks, I'm not kind of unclear, right? So the way I looked at this is I tried to find a pattern, right? So from 0, it looks like if I get 2 consecutive 1 bits, then I'll be divisible by 3. But then, if I get a third consecutive 1 bit, I'm no longer divisible by 3. But as long as I keep getting zeros, then I'll stay divisible by 3, right? So basically 2 consecutive 1s from two consecutive 1s from a state that was already divisible by 3 will get me back to a state that's divisible by 3, right? On the other hand, if I'm in a state that's divisible by 3 and I get a single 1 and then a 0, now I'm kind of in trouble because I'm kind of in this no man's land here. It's going to take me a while to get back to 1 that's divisible by 3, right? So if I get a 1, let's see, 0, 0, 1, I can get back, right? So I think what that means is that if I get a 1 here and then a 0, as long as I keep getting zeros, I'll stay non-divisible by 3 indefinitely, right? In order to get back from here, I have at least 2 cycles. I got to go 0, 1, right? So anyway, I came up with, I don't even know if this is right, actually, but I got 3 states. So if this is my start state, okay, my start state is I am divisible by 3. I got 2 other states that say I'm not, right? So if I'm in my start state and I get a 1 bit and then a second 1 bit, I'll be back, right? If I get a 1 bit but then a 0, kind of like if I'm here and I get a 1 and then a 0, I'm over here, which means I'll be over on this guy, right? Which would be state 2, right? Over here, I'll have a value of 2, right? And then how do I get back to 1 that is divisible by 3? Well, I'm in 2, I got to go 0 and 1. So I got to go 0 and 1, gets me back here, right? However, if I'm in 2 and I keep getting zeros, then, so that should be, that loop back should probably be a 0. No, that's right. If I get a 0, I'll come back here, I'll keep making this transition. Yeah, I'll keep alternating, right? Which is like having here, if I get 0, 0, 0. What I'm actually doing is alternating between these states. And depending on which one I'm in last, I can get back, I'm either 2 hops away or 1 hop away, right? Yeah, so I think that's right. Yeah, looks good to me. I didn't really check it. I didn't try it.
It'd be fun to see if it works when you get the tree expanded further.
Yeah, yeah. Or we could, you could type it in the chip dev too, and they'll test it for you. They have a test bench. So yeah, this is a question that they ask apparently at, I think, NVIDIA and Microsoft if you go for a hardware design job. Okay, now let's look at one final example that's relevant. This one's a little bit more complicated. This is another one I came up with. There is on FPGAs and in any ARM system like your phones, the on-chip network they use is called the they used something called the AXI bus. It's a bus that was originally developed by ARM. It originally was called the AMBA bus, and then they made it, AXI stands for AMBA Extensible Interface, I think. It used to be one of many. They used to have competition, but recently, in recent years, it seems like the industry has kind of, the embedded systems industry, anyway, has consolidated around AXI. You know, it used to be, FPGAs used to use the IBM Core Connect, bus, and then the Altera ones use Avalon. You can still use Avalon because Avalon's a lighter weight bus than this. But most of the, as far as I know, they used to have one called Hyper Transport, Rapid I/O. Texas Instruments has one called TerraNet. I think they still use that. But most of the high-performance embedded systems like you'd have on your phone, smartphone, would use the AXI, right, and tablets. So it's by far the most common one, but it's pretty complicated. So AXI is a master-slave bus, which means that each device on there can either be, or actually not each device. It's not based on device. It's based on the port. It's based on what port you have for a device. So you can have a device that has like 2 masters and 2 slave ports, depending on, and basically just master and slave just depends on which can initiate a transaction, read or write transaction. And this is a addressable, what do you call it? It's an addressable bus. You can read or write, right? It has a coordinate addressing system, right? So AXI has, and there's actually another version called AXI Lite that's a little simpler. But what I'm talking about here is the full AXI. This is the full strength AXI bus, and it has 4 channels. Sorry, five channels. 5 channels. It has a read address channel, a write address channel, a read data channel, write data channel, and a response channel. And the idea is that if I want to perform a read on the bus and I'm a master, I indicate that by putting an address out on the read address channel. And then, of course, that address will define one of the targets, slaves, on this bus I want to read from, right? Likewise, if I want to write, I put an address out on the write address channel, right? And then, of course, the slave, or the read address is the slave uses that to send the read response back. The write is used to send the write data to the slave. And then the response is the response to indicate that everything went okay. It's like an acknowledgement. However, the thing about this that makes it complicated is all 5 of these buses are arbitrated separately, which means that whoever's initiating the transaction has to indicate its intent to initiate a transaction, and then the other side has to handshake to move it forward, right? And it has to happen separately on all 5, right? So this is how it looks. This is actually a screenshot from the ARM website. So if I want to write on this bus, I have to put my address out on the write address channel. But before I can do that, I have to put the address out there, but I have to also say it's valid, right? And then whoever is answering to that address has to answer and say, oh yeah, I got me. That's me, right? And that is indicated by this address write ready, right? So you basically put the address out with the valid. So this is the master puts this, the slave then says ready for 1 cycle, right? This is what indicates that the intent to write has been registered and the address has been received. Now the address does 2 things. The address addresses a peripheral, right? But it also has a sub-address within the address space of that peripheral, like a register address, right? So you have to say, well, I want to write to the JTAG or the UART, because I want to print hello world. So I got to write to the UART interface, and I got to tell it that I got to target a specific register within the interface to tell it what I want to do in there, right? Okay, so then after you do that, I have to then send the data I want to write. So to do that, I have to put the I have to wait until I have to now switch to the write channel. I got a write data channel. And I have to wait until the target, the slave, announces that it's ready. And when it's ready, then I can put the data along with the valid, right? And there's also a last, which is used if I want to burst, if I want to send multiple beats of data, multiple cycles of data, right? In this case, there's just one word, one cycle of data. Make sense? And then I have to wait and make sure that everything worked. So then I have to assert, I got to go to the B channel, which is the response channel. I don't know why they call it B. I have to assert B ready, and then the slave will come back with a valid and a response code to say OK. Right? So it's complicated, right? So the idea is I got 3 different channels just for this one transaction, and all 3 have this dance that you have to go through, right? So what if I wanted, now this is actually quite common, because if you want to design a peripheral to connect to this bus, then you have to basically create the logic that will reconcile your application logic with the bus. It's like a bridge, right? You have to put a translator here that will translate your code in a simplistic interface here, like register file interface, but they'll translate that into the AXI language, the AXI protocol, right? And so this is called often called a bus adapter, bus interface, or a bridge, right? And the cool thing about this is if you can design this, then you can take pretty much anything you want and hook it into the AXI bus and have it talk to a world of other peripherals that can talk on that bus. It's like a common language, right? So in other words, in this class, we could add this to your processor, your CPU, and then your CPU could then participate in a system on chip, like the one that's in your phone, right? That'd be pretty awesome. Not only that, but we get access to all the pre-made IP that people made, like if you want to have pretty much any kind of I/O device, Ethernet, or say we wanted to have your CPU that you designed in this class talk to a monitor or an Ethernet adapter or a JTAG UART or anything. All you'd have to do is put this in, and then you open up that world of possibilities for I/O, right, for your CPU. We just, as you might imagine, I want to do that eventually, but I think it's a little too ambitious, for a 1 semester class. So I came up with a preliminary state machine, though, that will make this work. So the state machine basically has a state for each one of the steps that you have to take. So now the problem here is that keep in mind that the inputs to this state machine are actually a mixture between the application inputs and the bus inputs. Because, for example, to get things rolling, I have to wait for write enable to be 1. So this is my application logic. This is like your stuff. Like if your code wants to write something on the bus, it's going to announce that to the interface, the adapter, by saying write enable equals 1. At which point, this thing is going to go into action, and it's going to begin by requesting to send the address to the bus. So for that, it has to say address write valid is 1, right? But then it also has to send a busy signal back to the application side. So your stuff has to say, I have to tell you to wait while I do this bus stuff, right? So busy gets set to 1. And then I'm going to stay in that state until AW ready is 1, right? Now, you don't know how long it's going to take to get that. It may take, it's non-deterministic. It depends on what else is going on the bus, okay? So you'll wait in there until you get it ready, and then once you get the ready, you'll send the address, and you do that for 1 cycle, at which point you drop, you send the address, so you set the address, you set valid, then you wait for the ready to come back on the data write bus, right? So now we're done with the address, wait for the data, so we wait for write ready, at which point we send the data. To send the data, we put the data out, we put the W write valid and write last, because we're only going to send 1 word, not a burst. And then we stay there for one cycle, so we have an unconditional transition out of there. And then we wait for the B ready. I'm sorry, we set B ready, and we wait for B valid. Sorry, this is the response. And then we get the response. Now, the bus, the AXI bus may send back an error code. It has that ability through that response channel. So this state machine has an error state that it'll go to if it gets an error code back on the B channel. Make sense? So this is probably the most common type of state machine you would design. Although, like I said, if you create a multi-cycle arithmetic circuit or something like that, you need a similar type of state machine. Okay. Okay, and then I went ahead and I coded it in Verilog. Now this is only for writes. This is only for single word writes. This doesn't include the read logic either. Read logic is even more complex in terms of, I think it would take one or two more states, but maybe. But that's the code. And in this case, I used a state case statement there for the next state logic, and the output logic is there. So, typically you have to start with the state diagram and then transliterate that into Verilog, right? You probably wouldn't start with Verilog. You'd have to create that state diagram first. I think it'd be tough to just go straight into coding, right? Unless maybe if you're really good, you could do that. You could visualize it, right? Okay, any questions? Okay, good.